So now that we've talked about Java factory method operations, it's time to turn our attention to some of the aggregate operations that Java supports. So remember the way streams work. First, you take something that's not a stream, like a list or a map or something, and you turn it into a stream using a factory method. That's the first stage. And then the next stage is the apply stage, and that's where we have the aggregate operations. Actually, it's apply and combine. So those are called aggregate operations. So we're going to talk about the structure and functionality of aggregate operations in a stream, and this will start segueing us to some more specific details about cool methods. So an aggregate operation is basically a so-called higher order function that applies the behavior on elements in a stream. And higher order function is just a fancy schmancy way of saying a function that is passed a function as a parameter and may return a function as a result. So I don't know why people get so excited about the word higher order function, but there are certain programming languages that were known for doing higher order functions, Lisp being one of them. And now with all the cool stuff you can do with Java, with lambda expressions and method references, Java also supports higher order functions. The behaviors that are implemented with Java streams are implemented by lambda expressions or method references, and those, of course, are lambda expressions or method references to certain kinds of functional interfaces, like the function functional interface, or a predicate functional interface, or a consumer functional interface, or a supplier functional interface, and so on and so forth. And we'll talk about lots of examples of those things. You can go back and watch my video series on Java functional programming, which is on YouTube, if you want some refresher on what that stuff is. As we've mentioned before, what makes streams good? What are the benefits of streams? Aggregate operations can be used to form a so-called declarative pipeline that emphasizes the what, in other words, what computations we want to run, rather than focusing on the how, which is how the computations occur. Of course, the how is important. That's how things work. But when you're programming, it's often nice to not have to worry about the how, just focus on the what. Someone asked me a good question the other day on one of the discussion forums, which was, why can't Java just automatically figure out how to parallelize your code? And of course, it's sort of an ironic question. Java does that, right? So Java Streams is exactly that. Java Streams provides you with a framework where you say declaratively what you want to have done, and Java Streams figures out how to turn that into parallel code on your behalf. You don't have to write, you don't have to create threads, you don't have to synchronize threads, you don't have to wait for threads to do this, that, or the other thing. You don't have to use synchronization. It just works. What the poster really meant originally was, why can't I just write Java sequential code like a for loop and have it automatically convert it into parallel code? And the answer is, it doesn't work that way. And that's true of any language. You take any language where you write sequential code, like the sequential accumulator anti-pattern that we talked about, I think the first day of class, you're not going to be able to take that code and just automatically turn it into parallel code very easily. Sometimes, under certain conditions, with the right language with very limited semantics, you might do that once in a while. But that's really too hard for the optimizers to figure out. So much better is to write in a programming abstraction like streams, and then let the underlying infrastructure take the what and apply some pixie dust magic to convert that into the parallel how. And so that's what is going on with streams. There are two types of aggregate operations in streams. One type are the so-called intermediate operations, and these take a stream as input, do some processing, and yield a stream as output. And examples of these would be operations like filter, which we've talked about briefly, map, which we've talked about briefly, flat map, which we're going to talk about a lot more, which is a very cool operation, and then some other ones like take while, drop while, and so on and so forth. Interestingly enough, you don't have to put intermediate operations in a stream at all there's no necessity to do that. Now, it's almost often the case that you do it, but you could write something like this. You could say stream of, give a list of character names from the play Hamlet, and then just say .count. And that will return to you a count of the number of the characters that are in Hamlet. And like in this case, let's say there were 17 characters, that would give you back 17. With later versions of Java Streams, for reasons that I find a little odd, the semantics of count are rather odd. And I'm just mentioning this because I got tripped up by it one time. So it turns out if you insert a peek operation between the factory method of and the count, streams is perfectly legal to ignore peek. If it thinks that an operation has no side effect, it'll just ignore it. I have absolutely no idea why they decided to do that. It's very strange, and it broke earlier behavior. But you can read about this in this link and scratch your head and wonder why that's the case. So basically, newer versions of Java streams will optimize away the use of a stream, and it'll just directly count the number of elements. Very strange. That was an aside. That shouldn't affect anything we do in this class. It was just because I got burned by this thing one time, and I was like, that is really weird. So I decided to put it in my slides so I would warn other people about it. You can classify intermediate operations across several dimensions. And let's talk about these things here. One dimension is whether they're stateful or stateless. So stateful basically means that the information from prior invocations as the stream is processing must be used to figure out what to do with a future invocation. And here are some examples of stateful operations. Some of these operations are so-called run-to-completion operations. Every element in the stream will be processed. Other operations are so-called short-circuiting operations, which means that it'll stop after a certain point. So some examples that are run-to-completion would be something like sorted. We've talked about sorted before. Clearly, sorted has to buffer all the intermediate operation or intermediate values that come through from the stream at that point in order to sort them. Otherwise, how could you sort a partial stream? You have to get the whole thing. So that obviously requires state. There's other operations like distinct, which looks at every element in the stream and then only allows the ones through that are unique. So if they're duplicates, they'll be ignored. There's other operations that are so-called short-circuiting. So short-circuiting operations are going to only process a limited number of elements before they give up. So a good example would be limit. So limit needs to keep track of how many things you've seen so far in order to know when to stop. So that's an example of a stateful short-circuiting operation. And there's some other ones we'll talk about later, like take while and drop while and so on. Then there are also stateless operations. And these are ones that don't require any information from prior invocations on that stream. So these are really kind of, in my mind, the heavy lifters of streams. So you've got filter, you've got map, you've got flat map. Those are some of the ones you use all the time. And they just take a look at each element individually. They don't care what has come before. Each one works independently. And there are no short-circuiting stateless operations in streams. As a general rule of thumb, stateless operations typically require fewer processing steps, and they often require much less memory because you don't have to buffer everything up. And so as a result, whenever possible, you should stick with stateless operations, which doesn't mean you shouldn't use the other ones. It just means that it'll run faster if you use stateless operations than if you use stateful ones. And this is particularly true for parallel streams, as we were talking about earlier. So parallel processing makes a big difference in terms of how things work. And then the other differentiation we have is run to completion versus short-circuiting. So run to completion, as the name suggests, just means you go through the whole thing, you take a look at every element, and it processes all the elements in the input stream. And short-circuiting means once you have reached a certain threshold, like a count, or once a predicate fails or whatnot, then you will go ahead and stop processing at that point. So you short circuit, you don't process everything. There's also terminal operations, and terminal operations are the ones that will trigger the intermediate operations, which are the ones we just talked about, and then also produce a non-stream result. So if you ever want to look at the stream interface, which has a lot of methods in it, and you want to know, you ask yourself, gosh, how do I know if something's an intermediate operation versus a terminal operation? If it returns a stream, then it's an intermediate operation. If it doesn't return a stream, then it's either a factory method or it's a terminal operation. And here's examples of popular terminal operations. So for each, reduce, collect, find any, find first. Find first, by the way, is something you'll need to do for assignment number 1A when you're doing certain of the processing steps, such as perform crawl, you'll need to use find first, followed by or else. And that's because there's only one element there. And it just, a terminal operation, it just says take the first one. There's only one, so it takes the first one, which by default is the one because there's only one. Recall, as we talked about earlier, a stream must have one and only one terminal operation. There can be only one, for anybody here who's ever seen the famous movie The Highlander. So there can only be one terminal operation, and there must be one. If there's no terminal operation, the stream will never even run. As with intermediate operations, you can classify terminal operations across several dimensions as well. So we have the so-called run-to-completion operations, which process every element in the stream, unless, of course, an exception occurs, but let's ignore that. So modulo exceptions occurring, we process every element in the stream. So reduce, collect, for each, those are examples of terminal operations that are run-to-completion. And then there's also a whole bunch of short-circuiting operations, like all match, any match, find first, find any, none match. And these will cause the stream to terminate. They may cause the stream to terminate before all the values are processed. So for example, if you're doing find first and you've got 5,000 elements in your stream, as soon as it finds the first element, it's done. Likewise, things like all match, it says everything in the stream must return a Boolean true. And if it turns out for whatever reason that you get a false back, you might as well stop because they don't all match, right? So that would be an example of a short-circuiting operation. It'll just bail out as soon as that happens. And same for none match. You do none match as soon as you find a match, you can bail out because you know it failed. So that's the end of our quick overview of Java Stream aggregate operations. So we talked about run-to-completion operations, we talked about short-circuiting operations, we talked about stateful operations, we talked about stateless operations, and you don't have to completely memorize all those things because you can read the documentation to find it out, but you do need to have a good awareness of what kinds of operations you're dealing with in order to make sense out of the streams that you're reading when you look at code examples like the ones I provide, and then more importantly when you do your assignments, the stream operations that you're writing.